continue with the discussion that we started yesterday. We will arrive now this morning to present that theorem. So what is the point again? The point is quantum correlation, which are exemplified in their most important implications by by the entanglement, of course, and in particular by the prototype of entangled state, which is the singlet state of 2.5 particles. So one which can be on the left, the other one can be on the right, but they are in this correlated state. So just a summary of what we said yesterday. So outcomes of measurements are correlated at the distance. If I measure the spin up along a given direction, on the other side, with certainty, within of course experimental errors, with certainty the spin will be down and vice versa. And the question that Einstein raised is that, how can it be possible that you have correlations at the distance? Isn't that a sign of a non-local effect if you take them seriously? And the answer of Einstein is that no, you cannot be like that. The world is local, nothing can influence something else instantly or at a distance or at a superluminal velocity. Therefore, there should be an explanation, a local explanation of this quantum correlation. It's what now we call modern language local hidden variables. Einstein called them elements of reality, or the fact that the theory is incomplete. The theory doesn't give the complete description of the state of the physical system. Locality implies there is something more. And again, I present you the case of I also have the blue and the red ball, like Bassi in his lecture. In a box, the blue and red ball, correlation, because here I have the blue ball, on the other side there is the red ball. Classical, trivial correlations at a distance. But there is no mystery about that. It's just that the probability of the ball being in one box and the other one being in the other box is not a full, complete description of the state of the system. There is something more, which is the color of the ball. If you know the color, you can predict the color on the other side, and there is no mystery, no superluminal influence, nothing special. So this is, of course, quantum mechanics is more complicated than the blue and the red ball. But the bottom line, but the fundamental issue is the same. So the setup is, I accept locality, and then there must be what we are called hidden variables, extra variables capable of predicting the outcome of the measurement. So if you want to say it in a different way, the outcome of the measurement is already determined before the measurement, if you could control everything. So the outcome doesn't pop up. I don't know if I hope I can convey to you. If the outcome pops up at the time of the measurement, then you have non-locality, because here it pops up the spin up. And then how can here the experiment know that the spin was up in order to give a spin down? How can it be that by the measurement generating the outcome, if the measurement generates the outcome, how can it be that outcome up here gives outcome down there, if the outcomes are generated at the time of the measurement? This is non-locality. If they're generated, but they have to be generated in a correlated way, then they need to talk to each other. But they talk superluminally, it's non-locality, which is the bottom line. The world is non-local, but at the time of Einstein it was not like that. No, the world is local, so you cannot, if you generate here, then you have to transfer the information to the other side. And then the experimentalist here has to wait for the information to come, but that's not what quantum mechanics says. The other alternative is that the outcomes they are somehow already written there. They just show up during the measurement. It's like, again, the classical case of the blue and the red ball. The color blue is already written. When you open, you just see what is there, blue and red. But the two colors are there since the very beginning. Non-local and local, this is a local behavior. This is the behavior. We are trying to understand nature here. This is the point. If we stick that nature is local, but you want correlations, then there must be extra degrees of freedom, what are called hidden variables, that determine the outcomes of the measurement. And these are what we were left with yesterday. So the outcome of the measurement along direction A is determined once you know lambda, and of course given that it's a single state. It's either minus 1 or plus 1, and the outcome. Okay, so what are now? So Bell, so the point, Bell said, I want to use this to build a local model for the singlet state that so it's local, but that reproduces quantum mechanical predictions. Doesn't work. I cannot think of any model. Is that it is impossible to make such a model? The answer is yes, it is impossible. So I give you two versions of Bell's theorem. The first one is, to my knowledge, the simplest. The second one is the one that is typically you find on Wikipedia, probably in books. Now I have to move forward. This was yesterday, so here. So again, so we have the hidden the model where the local model, so the assumption is local. Remember that the EPR part of the story, locality means and quantum correlation. So we want to you want to have the quantum correlation. Locality means that there exists this extra variable. Okay, so I take these extra variables in the local model and I ask for the following thing. The probability that in the measurement, on the left along direction A, on the right along direction B, the outcomes are anti-correlated. So the outcomes are always anti-correlated if the two measure along the same direction. It's always anti-correlated. That's the single state. But here we are considering different directions. So sometimes they are correlated, sometimes they are anti-correlated. Here we consider the case in which they are anti-correlated. So it's a probability. So you have to sum, take the integral over the space of variables. So you have to compute basically the integral of the distribution of the hidden variables on the subspace of the full space in which you have anti-correlation. No? It's the game we played yesterday. But here in much more general terms. So that's the probability. Now we consider the following quantity. The sum of the three probabilities. The sum that the outcomes are anti-correlated along direction A and B, A on the left, B on the right, plus the sum of the probabilities that the outcomes are anti-correlated along direction B and C, now B on the left, C on the right, and finally plus the sum that the outcomes are anti-correlated along direction C and A, C on the left, A on the right. So it's a mathematical question. This is a very well-posed mathematical question. The sum of three probabilities. Note something that I said yesterday, the important thing of Bell's theorem, which, so you should appreciate that Bell was capable of going beyond Einstein. It's not easy to. No? You might want to try and hopefully we succeed one day, but doing better than Einstein is not something easy to do. Bell did that. Because Bell didn't focus on the striking fact, only on the striking fact that there are perfectly anti-correlation when you measure along the same direction, which is what everything tells you about the spin. When people tell you about the single state, the only thing that people tell you, I also tell you, is just the perfect anti-correlation. Bell went beyond that and considers the statistics also along different directions. That was the key point to arrive at non-locality, to take into account the full study. Okay, so we have the sum of the three probabilities. So, first step. Because now we use the perfect anti-correlation along the same direction. If B has so the outcomes A and B along the direction B are perfectly anti-correlated. also along direction C, perfectly anti-correlated, and also along direction A, perfectly anti-correlated. So I transferred, so the first line refers to probabilities for outcome A and B. Now I'm only probabilities for outcome A on the left. So this is, so here so far I use, so here the first line basically, the very writing of the line uses local hidden by locality assumption, just to set up the problem, so locality, up to here. EPR correlations for the second line. So the hypothesis I'm using. I'm done. The rest is mathematics, simple mathematics. So that's all I use so far. Locality and perfect correlation. Then it's a mathematical fact that I don't know how much you know of probability theory. This is just a property of the subadditivity of probability measures. It's pure property of any probability whatsoever, mathematics. That this sum of the probabilities must be larger, or at most equal to the probability of the union of the three sets. No? This is the set of all lambdas such that this is true. The union with the set of all lambdas such that this is true, and then no, I hope it's clear. It's just simple mathematical formulas. And then I don't know if it's easy to see. I will show it in the problem. That these probabilities work because one of these three events always happens. And just to convince you, I mean, then you think a little bit. But just to convince you, so if you have, this is the space of the hidden variable. Now let's see. Let's see if I'm good in counting. Let's see how I want to do it. Okay, so this is the space of the hidden variable lambda, which can be divided into these 8 subsets according to the possible values. So the lambdas determine the value is plus or minus 1. So this is the entire partition, the vertical one, the partition of the and this is A. Direction A and B refer to direction A, B, and C. So for some lambdas, the outcome will be all plus or all minus, or some plus and minus. You have all possibilities. So let's take the first one. What is the subspace where A? So A is equal to B. So it's this one. No, A is equal to B. This one, and this one. No? Here, for these values of lambda, so I should erase the middle part. The partition is just the vertical. So here A is equal to B, and then it's, so A is equal to, B is equal to C. B is equal to C is here. B is equal to C is here. It's here. And I am missing one, and it's here. And then C is equal to A. It's here. It's here. It's here, and it's here, and then it's here. No, I mean some mistake, whatever. So you see that the three cases cover the entire space. I hope you are following me. So the union of these three sets is the entire state space of the hidden variable. And the probability calculated on the entire space is 1. That's the end of Bassi theorem. So that's the end. So, moral, local hidden variables, and again, local hidden variables is not an assumption. It comes from locality. It's the first part of the story. If we believe it, so if the quantum theory, orthodox quantum mechanics, is non-local as a theory. You do something here, you change something there, because the wave function changes. Quantum mechanics is non-local. So, Einstein says, locality means there is something else to quantum mechanics. Local hidden variables. Call it with, you don't like the name, call it in a different way, but it's something different. Something more than the wave function. If you stick to the wave function as describing the state of the system, then quantum mechanics is not local. Okay, locality is the assumption. So locality implies hidden variables. And now Bell goes behind. Hidden variables, local hidden variables imply the inequality. Again, quantum mechanics violates. No, quantum mechanics is not local. Quantum probabilities violate the inequalities because it's not local. So you can just take as the three direction with the intermediate angle 120 degrees, then you can compute the probabilities of anti-correlated results. In the language of yesterday, is the probability of getting outcome plus or minus plus when you measure along two direction. The formula, you know, the formula was written in yesterday's slides. It goes with the cosine, and so you get 1/4. And 1/4 3 times gives you 3/4, which is smaller than 1. And so you violate Bell inequalities. Not surprising. Quantum mechanics, as a theory, orthodox quantum mechanics, is not local as a theory. Probabilities are affected. But, what is the content of that theory? Standard quantum mechanics is standard quantum mechanics violates Bell inequality. Can I replace quantum mechanics with a local theory that respects quantum probability? The answer is no. I hope you get the message. So, again, classical case. Blue ball, red ball. Probabilities are correlative, are non-local in that sense. Is that a physical non-locality? No, it's just a statistical correlation. I can replace this model, blue ball, red ball, with a perfect description where I know already the colors. And then everything becomes local. So these correlations are explained locally in an easy way. Can I do the same thing quantum mechanically? Can I explain quantum probabilities, quantum correlations with a local model? Bell says the following, that if I want to do this explanation with a local model, then the model will have to give me probabilities that satisfy the inequality. Okay, the local model has this property, no big deal. The point is that these probabilities will not be able to reproduce quantum probabilities, because quantum probabilities violate the inequality. So, again, the conclusion is that while classically I can reproduce classical probabilities of blue ball, red ball, classical correlation, I can easily reproduce these classical correlations with a local model, I cannot do that quantum mechanically. I cannot have a local model that reproduces quantum probabilities, because the local model will have to satisfy the inequalities, that's the theorem, but the quantum probabilities that should emerge from that violate the inequality. So there is no local model capable of explaining quantum probabilities.
Sorry, which version of the inequality was verified experimentally? This one or the CH?
The CHSH, which I will come now. I presented this just because it's as simple as it could be. So that's the main message, is that there is no extension, if you don't like the word in the variables because it sounds of mystery, fine. There is no way of extending quantum theory as a local theory capable of reproducing quantum mechanics. That's the best theory. So in that sense, quantum mechanics, quantum physics, if you wish, not just the standard formulation of quantum mechanics, any version of quantum mechanics, any theory of quantum physics must be non-local. If it is local, now we come again to experiment, if it is local, it's not quantum theory. It's a different theory which will make predictions which differ from quantum mechanical predictions. A local theory must be empirically different from quantum theory. Quantum theory is non-local. Then it became a matter of experiments. So it's not that no one said quantum mechanics is a theory made by humans. Quantum mechanics will realistically will fail one day. Quantum mechanics it's impossible. It's impossible. It's really would be outstanding that if in our development of humanity from the Big Bang to today, we were capable of finding the final theory of nature. And the final theory of nature is a quantum theory. That would be arrogant for us to believe that. Quantum theory is the theory of the moment, the theory that works very well. But it's reasonable to say that one day we'll fail in something, a new theory will come, like it happened with Aristotelian physics and then with Newtonian physics. The point is quantum theory failing here? Is quantum theory failing because of non-locality? That's the content of the experiment that started with Clauser and then went on with Aspect and then several other people to close different loopholes that I will tell you about. The outcome is that no, nature is on the side of quantum mechanics in this respect. Nature is confirming the prediction, nature confirmed many predictions of quantum mechanics, but in these experiments, and that's the value of these experiments and the right reason why they gave them the Nobel Prize, even if the motivation was not correct, but that's again, I'm upset with the Nobel Prize Committee, but the Nobel Prize is well deserved, there is no question about that. So that's the value of the experiment. They didn't check just any quantum property. Some electron structure is not any important property, but say not just some whatever properties. But they explicitly checked those quantum properties that leaded to a possible violation of Bell inequality. And they found the violation. The inequalities are violated in experiments, which means that our local model is a nice model. It's a beautiful model, but it's wrong as a physical model. Nature doesn't go that way. So Einstein was wrong in that sense. So it's not that Bell proved Einstein wrong, if you wish. It's nature that proved. As always, it's nature that commits when we do physics. And in mathematics, humans disprove other humans. But typically in physics, nature disproves humans. Nature, through Bell, and experimentalists of course, disproved Einstein. Locality is the wrong assumption. Yes?
Then what should we think about for special relativity for locality?
So can I postpone the answer to later, but I give you, so because I anticipate my point of view, I declare that this is my point of view, but then something more will come soon after that theorem at this respect. So now we tell you my personal point of view, and later I will tell you the accepted knowledge. My personal point of view is that at the end of the day, relativity and general relativity, special relativity and general relativity are wrong as fundamental theories of nature. Which, for general relativity, is not, so they are phenomenologically okay, there is no question about that. For general relativity, I don't think that it's much of a shock if someone says that general relativity is an approximation, because the systematic, well, someone calls it failure, let's say the systematic unhappiness, let's say, with the attempts to quantize quantum mechanics and quantum physics and gravity. So there is string theory of quantum gravity, there are gigantic frameworks, but seems still that is not the bottom line. So it's opening the possibility that you have to, the new theory is something different, so that also general relativity needs changes, apart from quantization, of course. There's some radical change. But I would say that the vast majority of the community of physicists would say that locality works, so special relativity works. That's a fact. The majority of the community thinks that. I believe that it's not the case. It's my personal point of view. That we have to, so that locality is a phenomenological, emergent effect. It's a thermodynamical effect. So just to give you an intuition about that. A gas at equilibrium cannot make work. No? You have to be out of equilibrium. So, locality, this kind of no signaling things, it is because we are at a sort of equilibrium. Bell inequalities testing the possibility of what happens if you are out of equilibrium. It's not thermodynamic, it's just an analogy. So that the world is non-local, but we are not capable of using this locality, or at least not today, because, we will never do anything fantastic like crazy science fiction thing that I don't believe. But I believe that there is a level of non-locality, of real non-locality, of real connectedness that cannot be exploited because we are in a sort of equilibrium. And so things balance each other, we cannot use non-locality. And locality emerges because of equilibrium. So equilibrium is an emergent property. So in that sense, physics has to be reformulated. But I will come back more on that after the next thing. Okay, so Bell's theorem, this is Bell's theorem 1. So now the Bell's theorem in the most popular version, which is the one that was most suitable for experimental verification. So there's two parties, Alice and Bob, with two spin particles, they are in an angle state, and then the rest you already know. So the key element now I'm trying to make it as general, the theorem, as general as possible. So before I use the EPR part of the story, I used so far, EPR that tells you if locality, hidden variables, inequalities, inequalities violated, non-locality. Now I skip everything, we start from zero with the general theory. The general theory, so deals with probabilities. So you can have a truly probabilistic theory, but it could be also a deterministic theory. P is just either 0 or 1. In the hidden variable version that I gave you before, I had a deterministic theory because the outcomes were, if you knew the hidden variables, they were predetermined with certainty. You get an outcome, you do not get an outcome. Here, I'm more open. It could be a deterministic theory, the probability is 0 or 1, or it could be a stochastic theory. The probability is whatever between 0 and 1. So A is the outcome on the left, B is the outcome on the right, so the probability that Alice measuring on the left gets the outcome A is always yes, no, now probably it's yes and no. yes, no, 0, 1, plus, minus, the important thing is two values. And the same Bob gets the outcome B, yes, no, plus, minus, whatever it is. If they measure along direction A for Alice and along direction B for Bob, given lambda. Now, pay attention, lambda is not the state of the system, so is the state of the system, is not necessarily taking variables. Is the state of the system according to your theory. So you make up a theory, the theory you want, I mean a decent theory of nature, not a crazy theory of nature. In a decent theory of nature, you expect that you have a state for the system. Otherwise, if you do not have a state of the system, then I mean, I don't know what we are talking about. So a kind of a common framework for any physical theory. So for example, we don't have to do quantum physics. We don't have to do quantum physics. Classical mechanics. Then lambda would be the position and momentum of the particles, for example. You can do standard quantum mechanics. Lambda is just the wave function. You can do hidden variables like Bohm mechanics. Lambda is the wave function and the position of the particles. You tell me, whatever it is, it's your theory. I'm just testing your theory. You give me the theory. A theory, of course, a theory that is capable of describing spin particles, and a theory that has a state. Not much to ask. Deterministic, probabilistic, you tell, it's your choice of theory. Now, I also define these probabilities. The probabilities for Alice to get the outcome A, measuring along direction A, the spin, when Bob does nothing. Bob doesn't do. And similarly, for Bob, when Alice does nothing. First were the joint probabilities of measurements. These are the probabilities of single measurement. Definition of conditional probability. So this is Wikipedia knowledge of probability. No, this rule over here for conditional probability. Probability of the joint measurements and the probability of conditional probability of two measurements multiplied standard conditional probability. Now comes the requirement. Now the request. Suppose that Alice and Bob may perform, so you have a state, possibly a single state, because that's the interesting one, and at space-like separated region, they make measurements. So they are, in a loose sense, instantaneous. They are space-like separated. And the request is the following one. Does your theory comply to this request or not? That's the request of locality according to value. What does the formula say? That the probability, the conditional probability for Alice to obtain a certain outcome, given that she's measuring along direction A, while Bob measures B and gets the outcome B, knowing the state of the system, this probability is the same one that you obtain by ignoring Bob. So that's a locality in a probabilistic, in general, in a probabilistic framework. That's a locality requirement. What, for Alice, what Bob does far away is not relevant. Whether he does something, measures along B and gets the outcome B, or whether it does nothing, is not important for Alice. Bob doing something or doing nothing will not affect Alice and its physics, her field, and vice versa. So this is the locality request. The statistics with the physics here, so it is physics, because if it's a deterministic model, it's the exact outcomes. If it's a probabilistic model, it's the statistical distribution. So the physics, the statistics here, is independent of what happens there. And vice versa. Then, because of conditional probability, you have the factorization of the joint probability, which is what also by this formula, I showed you this formula early in the morning. If two events are uncorrelated, the probability is the product of the two. No? The probability of having a lecture here and a music concert in Ankara, they are not related, or could be, In general, they are not related to each other. And so the probabilities factorize independently. So remember now, forget about quantum mechanics. We want just to inquire about nature. Can we make a local theory of nature that describes an entanglement, the correlating states? Forget about it. Try to forget quantum mechanics. Doesn't exist. Yes.
Sir, I have a question. Can you define local and non-locality in simple words because I got confused between local and non-locality.
Something local in physics. Locality means that what I do here cannot influence instantly as something else. So I move it, so I am talking to you because I change the air here, the wave propagates at finite speeds and reaches you. So it's a finite influence, a finite propagation. If I tell you, run away because there is a fire, it's not instantly. You have to wait for my voice to reach you and then you will start running away. This is locality. Locality in physics, which is a pillar of modern physics, is that anything that happens here needs a finite speed to propagate elsewhere. Non-locality means that it's telepathy at the end of the day. What I do here can change things on the opposite side of the world immediately. Instant, well, faster than the speed of light, let's say, but when you go faster than the speed of light, it's like instantly. Clear? So this is locality.
So in non-locality, speed is not in charge.
Sorry?
Speed is not in charge in non-locality.
Is not?
In charge, like we don't use speed.
Yes, in non-locality, basically there is, so technically speaking, in non-locality, you can have a speed faster than the speed of light, which is believed to be the highest possible speed. But when you are faster than the speed of light, there is no limit, and then it could be without speed, instantaneous, infinite speed. Like in classical mechanics, Newtonian mechanics is formulated that way. No? If you take the Coulomb potential, 1 over r, if you move the particle here, you instantaneously move the particle there. Then we know that this story. So I hope you are following me with locality and non-locality. So again, forget about quantum mechanics. We are redoing physics, and I'm making a principle. Can I build a theory? We are building a theory of nature, a local theory of nature, capable of describing the correlation. Any theory. The request is locality, formulated in this sense. Now, just to show you, I don't know if you have seen it, but just for to show you the theorem, and then you find it in many books. Then you define this quantity here. So I will go a bit fast because it's just mathematics now, but it's useful also to see the proof. So it's the sum of agreements. Yes, now it's yes and no. Sum of agreements, like plus and minus. Sum of agreements minus the sum of disagreements along two given directions. Probabilities, probabilities of agreement minus the probability of disagreement. This is just a definition. Here is that you use the locality condition, and then this thing, you can use the previous formula, factorize it like that. The product of two products. Just locality. Then you can take the difference between this expectation along two directions A and B, and along A and D. Well, you just get it. Nothing. You can then play a little bit and do some minimization, and then since these are probabilities, so the sum must be 1, because the outcome is either yes or no, it's either plus or minus, so you can write this as 1 minus 2 times the probability is something that is in between -1 and +1, so you can end up with this inequality. So the modulus of this is less than, so this is, the modulus of this is just 1, so you can ignore it, is less than this one. Expectation AB minus expectation AD, you repeat the same game, expectation CB plus expectation CD. You know, again, we are using 4 different directions, AB, CD. So there the theorem was simpler, it was along 3 directions. Now it's a little bit more complicated, it's 4 directions, but it's more directly applicable to experiments. And again, I want to stress the importance of the analysis of Bell, different directions, considering the statistics along different directions. Okay, so the quantities that I put in braces are as they are, since they are between -1 and 1, this I don't show you. You can easily prove that, it's just mathematics, trivial mathematics, just to think a little bit, that given these 2 numbers, that are between -1 and 1, then the following inequality holds. It's a simple property of numbers between -1 and 1, and then you end up with this. So this is the thing, the point. So your theory. So I'm simply repeating what I said before, but because that's an important message. So now it was not, again, EPR, locally the variables. The game has changed a bit. The game is, give me your theory of nature. Build the theory you want for the spin particles, for at least 2 spin particles. Build the theory you want. Now, do you want your theory to be local or not? Typically, you would say yes, because we believe in special relativity, we believe in locality. So I take a local theory. Local theory means that for space-like measurements, you should have independent outcomes. Because that's not locality. That's locality. What happens here cannot influence faster than the speed of light what happens there. So the physics here is independent from the physics there, if it's space-like separated. Special relativity. So probabilities factorized at the end of it. Factorization of probabilities implies this inequality. So this is mathematics. This is not that you can argue with that. So if you have this, mathematics, that comes out. So your theory that obeys locality must satisfy Bell inequality. Clear? So the statement is any local theory. I'm not talking about hidden variables anymore. Any local theory in this sense where lambda is the state of the system, that the theory tells you for the state of the system. It's your theory. I'm just checking your theory, not beating my theory. If it's local, then it satisfies the inequality. If you quantum mechanics, now we take one theory, possible theory, standard quantum mechanics. Lambda is the wave function. It violates the inequalities, but because it violates locality, that's clear. So standard quantum mechanics violates. No, wait, I can't. So as a theory, it's a non-local theory, but that we knew from Einstein. But can we have a different theory? The question again, you know the question. The experiment said no. The experiments have been done. The inequality has been checked. It's violated. So no, you cannot have a local theory. If you make a local theory, and there are people that from time to time try to publish papers about local theory of quantum physics. They're wrong. Okay, the testability. So now we want to give an experimental content to this inequality. So as it is, the inequality is beautiful, but it's a bit dangerous because in order to compute experimentally this quantity. So E, remember, E is the sum of probabilities. In order to compute E, you need to know P. But to know P, you need to know lambda. And you might have considered a theory where the state is given, but is not always accessible. So think again of statistical mechanics. If you talk about the gas, the state of the gas, according to classical mechanics, is the position and velocity of all particles in the gas. I mean, theoretically you do that, but experimentally you cannot access that. So you cannot access the true state of the gas. You have to accept that, sorry? You have to accept that you know only, and you have a partial knowledge, the temperature, the pressure, the volume, and not the full state. So as they are, you cannot use them experimentally because the state could be inaccessible practically. Well, okay, fine. So we divide the variables in controllable and uncontrollable degrees of freedom. So, but
can we do it for trapped ions?
sorry?
If we have some trapped gases or trapped ions, can we do it? Trapped ions.
Can we do what?
The last slide, so as you see that, for example, we cannot able to mention the particles of the gases because they are in random motion. But in case of we have trapped ions or trapped gas, so, or cold gas, can we do it or not?
Well, you also for the you never have a perfect control of the gas of cold atoms. So you have an extremely good control, but it's not a perfect control. So also there you have to trace away something that you don't know. Maybe it's less than it would be with the classical gas, but still there is something. So here I'm taking into account the possibility that you do not have a perfect control, but some good, excellent, but not perfect. So you can control part of the system, but you cannot control the totality of the system. And therefore, what you have to do, you have to average what you do also in quantum mechanics. When you don't do average. You do statistical average over the trace at the end of the day, over the uncontrollable degrees of freedom. So, instead of using the full lambda, you average what you don't know in order to have something that depends only on what you know. So now it's E of mu, not E of lambda, E of mu, where mu is the experimentally controllable degree of freedom. Then what happens? Starting from the previous line, the inequality with lambda, simple calculation, you can prove that the same inequality holds. I don't want to go through it simple, it's just a majorization again, even with mu. So now that E is in terms of mu, which is what you can control. Now the inequality, the Bell inequality, is expressed in terms of something that is experimentally accessible. Mu is the experimentalist will tell you, look, I can control this part of the system, but not the rest of the system. And we call it inequality. Okay, so this is a quantum mechanics that violates Bell's inequalities. I don't want to go into this, and then that's a list of, not exhaustive list, of experiments that have been done that prove now in an unambiguous way that Bell inequalities are violated in nature. Nature is non-locality. So one has to be careful. What does it mean, non-locality? No, it's, how much time can I go on before people die here? Do I have now it's 12, I have a few minutes, then I will stop. Non-locality, usually with non-locality, people think of instantaneous signal. It doesn't have to be like that. Non-locality means also that if I kick a stone here, for some magic, then something jumps up over there. It's a kind of a dubious theory, but take a theory like this. I kick here and then the rabbit jumps there, but with no influence. But every time I come in, every time I kick, the rabbit jumps. This is a non-local theory. This is an example of non-locality. Of course, then you ask the question, why does the rabbit jump every time that I kick the stone? Then it's unavoidable to ask the question. Bell's theorem says that whatever the answer is, the answer will be it's a non-local phenomenon.
So, in non-locality, can we think about parallel universes, for example?
Well, yes, but like in locality. I think that the two topics are not connected. You can have parallel, in both cases I would say you could have parallel universes. They are parallel, so they don't influence each other. And they could be local or could be non-local. So I'm not sure.
Like, do we have something in non-locality which includes in parallel universities? Universes? I mean, in this universe, I make something that affects the next universe, which is parallel to me.
Well, that is a different story. So, yeah, so okay.
Is there an assumption like that?
No. So the assumption here is that there is only one universe. And the universe is non-local. Then, if you wish, you can have other universes which might be connected. But that's an addition to the story. Here the story is that there is only our universe, and our universe is non-local. Yeah? It was you. Yeah.
Do we need new physics such that Newtonian physics destroyed the Einstein physics since non-locality?
Okay, so I will give you the historical, the state of the art later, but I give you my personal answer. But my personal answer is yes. My personal answer is that you need a new physics, and I give you a motivation for that. In classical physics, so non-locality, and then I will stop here. Non-locality is not something new from quantum mechanics. Non-locality is there also in classical physics. The Coulomb force is non-local. So Newton didn't like the Coulomb force because of non-locality. But there is and the Coulomb force has been replaced by let's talk about both in the case of gravity and electromagnetism. It has been replaced by a field. Has been replaced. No? The Coulomb force. So that according to Coulomb, if you have two masses, so to take Newtonian, Coulomb is Newton is the same one, where are the potential. If you take two masses and you move a mass here, you instantly change the position of the mass there because of one curve. And then with general relativity, we know that this is an approximation. What happens in reality is that when I move the Earth, a gravitational wave moves, goes here, and tells the other mass, look, that mass moved, you will have also to move. So it's a local thing. First. So, but this is a non-locality of the theory, Coulomb, which has been replaced by a local theory, and then nature proved the locality of the interaction. No? So the logic was, the theory is non-local, Coulomb. It was replaced by a local theory, general relativity. Nature confirmed general locality. Here, it's a different story. Here. The theory is non-local. Can we replace it by a local theory? Bell's theorem, test of Bell's theorem? No. We cannot replace it by a local theory. So the history went differently. For Coulomb, nature proved that we can replace non-local Coulomb with a local thing. For entanglement, nature proved that we cannot replace it with something. So it's non-local. You cannot do anything. Now, there is a very important difference. So, coming back to the relation with Coulomb, there is a very important difference between quantum non-locality and Coulomb non-locality. Coulomb non-locality, so this is again my personal opinion. The Coulomb force goes with the distance, the force in the inverse of the square of the distance. So it bears the notion of space. Coulomb, although being non-local, acknowledges whether two masses are close to each other or are far away from each other. If they are close, the force is stronger. If they are far away, the force is weaker. So the Coulomb force bears a notion of space. Quantum non-locality in the form of entanglement is, as far as we know, independent of space, of distances. It doesn't decay with the distance. It stays constant. It could be experimentally more challenging, but it is constant, independent of distance. Whether the two particles are here and or in the next room, tested experimentally. Whether they are here or in orbit, tested experimentally by the Chinese with the Michus satellite. And as far as we know, whether one particle is here and the other one is on the opposite side of the universe, the correlation doesn't decay. So entanglement is insensitive of distances, it's insensitive of space. And my point, my take, is that means it's an indication that space is the space as the Newtonian, or also the general relativity, the Newtonian or general relativistic container of physical phenomena is not a fundamental entity. So in that sense, you have to redo physics. Space is not fundamental. People are doing that. There is relational physics. Barbour and other people, shape dynamics, singulars, shape dynamics. It's a theory where space is not fundamental. Only the relative configurations are part. So that is my take about that. So that quantum locality is an indication that basically we are understanding nothing about nature. Which, if you give a perspective to history, is not surprising. Do we really believe that now we are the geniuses that we understood anything, and people before us were just silly, and people after us will be jobless? No. We are in the stage of long development in our understanding of nature. At least it's my take on that. So I stop here. I will tell you about conspiracy theory, which is something nice. Okay, thank you for the attention.